Welcome students to the MOOCs lecture on fuzzy sets, arithmetic and logic. This is lecture number 22 and as you all know, in the last class I started fuzzy logic. We have seen that the basis of propositional logic that is each statement can be given a truth value either one that is true or 0 that is false is not practically justified. To stress the point further, I give you another interesting example. From logic known as liar paradox. So, there are many versions. I take a simple one. So, liar paradox. Suppose I make a statement S, and what is the statement? The statement is that what I am stating is false. Question is, what is the truth value of S? So, we know as per propositional logic, S can have two truth values, true that is 1 or false that is 0. Suppose S is true, that is truth value of S is equal to 1, implies my statement S is true, implies what I am stating is false, this is true, implies what I am stating is false, implies S is false implies truth value of S is 0. Thus, starting with T s is equal to 1, we get T of S is equal to 0. Conversely, suppose S is false. This implies T of S is equal to 0, implies what I am stating is false. This statement is false implies what I am stating is true, implies S is true, implies T of S is equal to 1. Therefore, starting from T s is equal to 0, we get T of S is equal to 1. From the above two cases, we get T of S is equal to 1 implies T of S is equal to 0. Therefore, T of S is equal to 1 implies 1 minus T of S is equal to 1. Therefore, T of S is equal to 1 minus T of S implies 2 T of S is equal to 1 implies T s is equal to half. This says that we need to go beyond propositional logic to derive new facts or to infer from given set of facts one possible extension is multi-valued logic. Here, truth values are not only 1 or 0, it can take other values also. The simplest form of multi-valued logic is 3 valued logic. Here the truth values are 1, half and 0. Many researchers have given their interpretation with 3 valued logic, but the most popular one is by Logic-22 in the 1930s. The main problem here is that how to assign truth values for all the logic operations in particular and, or, and implication. Since there are 3 values, given 2 logical variables A comma B, we can have 9 possible pair of values. One one, 1 0, 0 1 and 0 0. These 4 we have already seen. The new 5s are 1 half, half 1, half half, half 0 and 0 half. How to assign truth values for these? So, Logic-22 has given the following: A complement is equal to 1 minus A. Therefore, complement of half is equal to half. A and B is equal to minimum of A comma B, and A or B is equal to maximum of A comma B. Therefore, with respect to the 5 pairs, 1 half, half 1, half half, half 0 and 0 half, we have and is equal to minimum. Therefore, half, half, half 0, 0 and or is equal to maximum, that is 1, 1, half, half and half. The question is, what about implication? We need to find a mathematical formula that satisfies the 4 values for propositional logic. Therefore, if we have two logical variables A and B, then for the 4 pairs one comma 1, 1 comma 0, 0 comma 1 and 0 comma 0, we should have the following. A, B, A implies B, 1, 1, 1, 0, 0, 1, 0, 0 and 1, 0, 1, 1, because that is the truth value of A implies B when we work with propositional logic. Therefore, when we are in the domain of multi-valued logic, we need to get a mathematical formula that should give the above 4 values for the aforesaid pairs. And at the same time, the same formula should be applicable for other truth values. Since we are working with three valued logic, with possible truth values one, half and 0, then A implies B formula should be such that for 1 0 for 1 1 1 0 0 1 and 0 0, it will give 1 0 1 1, and we shall use the same formula for 1 half, half 1, half half, half 0 and 0 half. The problem is there may be more than one function for the same task. For illustration, suppose we use A implies B is equal to not A or B. Second formula is A implies B is equal to minimum of 1 comma 1 minus A plus B, and suppose a third formula is A implies B is equal to maximum of 1 minus A comma minimum of A comma B. Let us examine these three formulae. 1, A implies B is equal to not A or B. So, we have A, B, not A, not A or B. So, let us see with respect to the 4 pairs, if A is equal to 1, B is equal to 1, not A is equal to 0, therefore, not A or B is equal to 1. If A is equal to 1 and B is equal to 0, not A is equal to 0, therefore, not A or B is equal to 0. If A is equal to 0 and B is equal to 1, not A is equal to 1, and therefore, not A or B is equal to 1 or 1 is equal to 1, and if this is 0 and this is 0, then not A is equal to 1, and therefore, not A or B is equal to 1. Therefore, for these 4 values we get the correct answer. So, let us do for the remaining 5. So, we take 1 half, therefore, not A is equal to 0, and therefore, not A or B is equal to half. In a similar way, half 1, not A is half, and we get or 1 and half by taking maximum, it is 1, half and half. Therefore, this is also half, and by taking odd we get half, half and 0 we get half, and therefore, this is also half, and 0 and half, this is 1. Therefore, taking maximum we get 1. So, these are the 5 values that we obtain for these 5 pair of truth values A and B. Let us now consider the second formula. A implies B is equal to minimum of 1 comma 1 minus A plus B. As before, we draw the table. And these headings are A, B, 1 minus A and 1 minus A plus B. So, let us see what happens with the values. So, A is 1, B is 1, 1 minus A is equal to 0. Therefore, 1 minus A plus B is equal to 1. Therefore, minimum of 1 and 1 minus A plus B is equal to 1. When A is 1 and B is 0, 1 minus A is 0. Therefore, 1 minus A plus B is equal to 0. Therefore, minimum of 1 and 1 minus A plus B is also 0. 0 and 1, 1 minus A is equal to 1. 1 minus A plus B is equal to 2. Therefore, minimum of 1 and 1 minus A plus B is equal to 1. When this is 0 and B is 0, then 1 minus A is equal to 1. Therefore, 1 minus A plus B is equal to 1. Therefore, minimum is 1. Therefore, we find that we get the same values for the known pairs. What happens for the other 5 pairs, namely 1 and half, half and 1, half and half, half and 0, and finally 0 and half. Therefore, 1 minus A is equal to 0, half, half, half and 1. Therefore, 1 minus A plus B is equal to half, 1 minus A plus B is equal to 1 and half, 1 minus A plus B is equal to 1, 1 minus A plus B is equal to half, and 1 minus A plus B is equal to 1 and half. Therefore, if we take minimum with 1, so I get half, 1, 1, half and 1. Therefore, we get these 5 values here. The third function, A implies B is equal to maximum of 1 minus a minimum of a b, and if we draw a table a b 1 minus a minimum of a b and maximum of 1 minus a comma this minimum of a b. So, what is going to happen? We have 1 1. So, 1 minus a is 0, therefore, minimum of a b is equal to 1, therefore, maximum of these two is 1. 1 0, 1 minus a is 0, minimum of a b is equal to 0, therefore, maximum of 1 minus a and minimum of a b is equal to 0, 0, 1, 1 minus a is equal to 1, minimum of a b is equal to 0, therefore, maximum of these two is 1, and 0, 0, 1 minus a is 1, minimum of a b is equal to 0, therefore, maximum of these two is equal to 1. So, we get the same set of values. Now, we can extend it for the 5 pairs 1, half, half, 1, half, 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 0 and 0, half. Therefore, 1 minus a is equal to 0, half, half, half and 1, and minimum of a and b is equal to half, 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 0 and 0. Now, we have to take maximum of these two, it is half, 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 half and 1, and we see that we get another set of values which are different from the earlier ones. Thus, we have several possible choices for A implies B. For multivalued logic, Lukasiewicz proposed the formula minimum of 1 and 1 minus a plus b to compute A implies B. Note that the above formula can work for any arbitrary values A and B belonging to the interval 0, 1. In our discussion, on drawing inference from conditional statements we shall use Lukasiewicz formula to compute A implies B. A natural extension to 3-valued logic is n-valued logic. Which is called ln, and the truth values are 0, which is equal to 0 upon n minus 1, comma 1 upon n minus 1, comma up to n minus 1 upon n minus 1, which is equal to 1. Thus, one can assign n possible truth values to a statement. As n goes to infinity, it covers all rational numbers in 0 to 1. One can use Lukasiewicz formulae to obtain the truth table. Now, propositional logic is helpful to validate an argument from a given set of premises to the conclusion. We cannot use propositional logic to establish the truth of a proposition whose premises are not given. For example, all men are mortal Ram is a man. Therefore, we can infer that Ram is also mortal. But such an inference cannot be drawn using propositional logic. Because it does not analyze the internal structure of all men are mortal. So, to propositional logic, all men are mortal is one statement which can be true, can be false. It does not go inside to tell us that we can use this statement to justify that any particular person is also mortal. And this is because all men covers all the people, and therefore, to infer about each individual, we need to use some variable x, so that we can instantiate the value for x with some particular person, and therefore, from there we can infer that he is also mortal. This internal analysis of the structure is not present in propositional logic. Hence comes the need to extend the gamut of logic, in particular with the introduction of variables. The next level of logic is called first order predicate logic. So, what is a predicate? A predicate is a Boolean function applied on some set x, that is p is from x to 0, 1. Say for example, x is equal to the set of numbers 1, 2, 3 up to 10, and suppose the predicate p of x is equal to x square is greater than x plus 10. Therefore, when applied to the above set, we get P of 1 is false, since 1 square is not greater than 1 plus 10. P of 2 is equal to false, since 2 square is equal to 4 is not greater than 2 plus 10. P 3 is equal to false, since 3 square is equal to 9 is not greater than 3 plus 10. P 4 is equal to true, since 4 square is equal to 16 is greater than 4 plus 10. And now we can see that till P 10 it is true, since 10 square is equal to 100 is greater than 10 plus 10. Thus, a predicate when applied to the set elements then for each x belonging to x, P x becomes a proposition. That is, it becomes a statement which says it is true or false. In a similar way, we can have binary predicates. For example, P x comma y is x is greater than y. If we apply on the same set, say 1, 2 up to 10, then we can see that P of 10 comma 1 is true, P of 1 comma 2 is false. This is because 1 is not greater than 2. This is true because 10 is greater than 1, and like that can be obtained for all possible pairs. Predicates allows us to use variables on its domain set. For example, let X be the domain set of all men. Therefore, consider the predicate man. So, when we say man John, that is, we want to state that John is a man, it is true. If we say man Mary, then it becomes false, because Mary is not a man. Now, suppose we want to state all men are mortal. So, we define another predicate say mortal x, which is true if x is mortal, which is false if x is immortal. Now, to state all men are mortal, the focus now should go to this quantity all. It is covering all the elements of the set X of men. Such a quantifier is called universal quantifier. As it assigns truth values for every element of the set X. The universal quantifier is denoted by this symbol, which means for all. Therefore, to state all men are mortal, we can have the following logical expression. For all x, man x implies mortal x. Similarly, suppose we want to state all boys are tall, we can write for all x, boy x implies tall x. Now, suppose this is not true. So, we want to see its negation. What can be the negation? The negation of all boys are tall is not all boys are not tall. This is not the negation. The negation is there must be at least one boy who is not tall. That is, there exist x, boy x and not tall x. So, this gives another quantifier. This is called existential quantifier. This will be true if there is some element, say x, in x such that p x is true. We can combine these quantifiers in many ways. Suppose we want to say all men are taller than all women. So, we can write it as for all x belonging to x, for all y belonging to y, taller x comma y. On the other hand, suppose we want to say for any man there is some woman so, let me call it x, let me call it y, such that y is taller than x. Then we can express it as for all x belonging to x, there exists y belonging to y such that taller y x. Question is, how to get truth values for quantifiers. There exists x p x, its truth value is or x belonging to x p x. That means, if for any one of the elements of x p x is true, then there exists x p x is going to be true. On the other hand, for all x p x is true if it is true for all the elements of x, therefore, its truth value is going to be and x belonging to x p x. That is, if for all the elements x p x is true, then for all x p x is going to be true. So, before we stop, I give you a canonical representation. If we notice that all the statements are sentences in a language. So, if we say man x, it implies x is a man. In a similar way, tall x implies x is tall. So, canonical representation of such statements is x is p, where p is a predicate. In a similar way, x is Indian is essentially we mean x is a citizen of a country. Therefore, the canonical form may be x is p of y, where x belongs to x set of persons, y belonging to y set of countries, and p is a binary proposition. Okay, students, I stop here today. In the next class, I shall start with fuzzy proposition. So, in these two classes, I have given you the basics of first order logic and propositional logic. Of course, logic has been extended to much more theoretical details. We have para-consistent logic, description logic, default logic, diffeasible logic. There are many different forms of logic that has been developed theoretically. For this course, we shall look at fuzzy logic and we shall see how we can make inference from fuzzy logical propositions. Thank you.